Hello, my name is Hakon and welcome back to my channel where today I'm doing another little tutorial on the Empress effects Zoia. The Zoia, of course, is the modular patchable digital synthesizer in a little box with a unique grid interface and where the only limitation, most of the time, is your imagination and the CPU. And today I'm going to talk about LFOs. And there's a clue, of course, in the title of this patch. An LFO is a very, very useful module on the Zoia. It's a low frequency oscillator, that is to say, an oscillator that doesn't go or isn't intended to move at audio rates to produce audible waveforms, but it is slow and intended to be a variable cyclical control voltage source for controlling parameters, for triggering events, etc., etc. You can use it for so many different things. It's very hard to almost to make a patch of anything and not use an LFO. It's also a brilliant module to use if you are using the Zoia to control external gear. Very often LFOs add a lot of flavor because you can use them to vary a parameter over time in different waveforms. If you have been using LFOs on the Zoia, you might be familiar with the fact that they have speed up to 2,400 beats per minute, which means cycles per minute. So that is full cycles from 0 up to 1 down to 0. And 2400 is the fastest you can do in the LFO module itself. I did make a patch before, quite a while ago, in August, I think, where I demonstrate a way to make it go at, if I remember correctly, 12,000 beats per minute, which is very close to the theoretical fastest speed you can get a gate trigger to work on the Zoia. I'll put a link to the video up here. So that's the fastest you can do, is about 12,000 beats per minute. But what is the slowest you can do? If you have been using an LFO, you might have looked at it and seen that the slowest time you can set an LFO to, and that is the one that is next to infinite. So you have infinite here, and you press shift and you do one click on your encoder and you get 8,830.113 seconds, which sounds like a really long time, but if you look at the output here, it's moving a little bit too fast for that to be a cycle of 8,800 seconds. In fact, if you set an LFO to 88 seconds and you compare the outputs now, so there we go. So here we are. This is one that's set to 87.74 seconds, and now it's 46, 45, 44, 43, 41, 40, 39, 38, 37, 36. Yeah, they are actually identical. The slowest speed you can get on an LFO on the Zoia is 87.74 seconds per cycle. And if you set it to anything slower than that, it stays at that same speed. So how do you make an LFO that is slower than 87.74 seconds? There are many times that conceivably you may want to do this. For instance, if you are working with generative, ambient, slow ambient music, you want to create changes that happen over a really long time, very slowly, and this kind of speed may be too fast. So how do you do that? I'm just going to remove these modules down here now because they are not part of the patch. They were just here so I could demonstrate the speed of the LFO there. This is the patch. This is the algorithm that creates a slower LFO. But before I show you that, I'm going to show you on paper my train of thought, because one of the things I want to do in my tutorials as much as possible is to explain not just the result, how the patch works, but also a little bit about my thought process and how I got there. And this is something I hope will be useful to you as you do your own patches on the Zoia and do your own problem solving, and as you find your own sort of ideas for things you want to do with the Zoia. It gives you an extra more tools for your toolbox, as it were, that will help you in problem solving what you've tried to achieve. So I'm going to put a piece of paper here, and I'm going to have to move my light a little bit, and I'm also going to refocus my camera. Okay, so triangular waves is what we are going to concern us with today. So we are having well, let's just, for simplicity's sake now, say instead of 88 seconds, we are using 60 seconds for a cycle. So this is the waveform of a triangle wave, LFO, and there's two of them actually. And we have here 1 minute and 1 minute. So 2 minutes for this, for it to cycle through this twice. And my thought process was, how do I make the Zoia double the length of this cycle? So I turn this two waveforms like this into this waveform. So let's just do like so. And I did draw this up when I was thinking about this, because it makes it quite easy to see what you want to do. So we got 0 here, and we got 1 there, and 0 again. And what needs to be done here is that when we reach the peak of our waveform, when it reaches 1, we want to invert the phase so that instead of going down, it keeps going up. And when we get to 1 again, we want to go back to normal polarity. So we want it to go down again, exactly as the LFO output tells us to. So how do we do that? Well, that's one thing we have to do. That's another thing we have to do as well, in order for this to work, of course, is that this point that says 1 needs to be reinterpreted at the output as 0.5. So 0.5, because we still want to keep going up. So, and this new peak here is what's going to be a value of 1. And then 0.5 and 0. So that's two things really we have to do to achieve that. So we have to reverse the polarity between 1 and 1, and we have to reduce the output, or the value output, so that 1 becomes 0.5. Okay, so what we need then is, first of all, to detect when we get to the peak. So we need something that detects that we have reached a value of 1. And when that detector has triggered, we need then to invert the value, and we have to add, if you look at this like this, to add a value of 0.5 to the output as well. So if you look at this, so we have this triangle here, and then it needs to move in this triangle there, and then back down again here. So, and then it moves like so, of course, for that triangle there. Okay, so those are the things we need to do in order to achieve this. Now, before I say anything about how that works, I'll just quickly say something about why I've chosen triangular waves now, because if you see this particular method of doing it, there may be other ones. I always like pointing out this, that there's one possible way of doing this, but this way works predictably. Well, it works predictably with other waveforms too, but the thing is that if you want to maintain the same shape waveform, this only works with triangle waves. And I'll show you why. For instance, if you have a sine wave here, and what happens if you take the peaks here at 1 and you invert the phase there, you get this kind of shape. So that is the waveform you get if you do this with a sine wave. And another thing I wanted to do as well was that once I've done this, once I've created a new wave that is now 2 minutes long, I want to be able to do the same again. So I want to take the output and treat that as if that was an LFO starting the whole process, and do the same with that again. And that also is a constraint on how I construct the patch, because there are some things I cannot do to make this happen if I want to do the same with the value module as a starting point now for this second bit. And then I do this again, and it becomes 4 minutes, etc., etc. And I can do the same process over and over again to double the length of time every time. So that is my thought process when I was thinking about how to construct this thing, and also the main sort of design idea behind it. So how is this constructed on the Zoia itself? Starting, of course, with an LFO, and it is set to triangular wave, and it is set to 1 beat per minute. So that is 1 cycle per minute. And there's no reason specifically why it has to be 1 beat per minute, but it makes it easier to calculate the end length of wherever we get to. And the output of that LFO goes to a few different places. It goes to a comparator over here. It goes to an inverter here, and it goes to a switch. I'll start with the comparator first. So in my illustration, I said I want to detect when this reaches its peak of a value of 1. And the way I do that is by sending the value output from this LFO into a comparator. What a comparator does, it has 2 inputs. They're known as the positive and the negative input. And this is the positive on the left and the negative in the middle. And as long as the value in the positive input is equal to or greater than the value in the negative input, then it will output a value of 1 on the output pad here. So if you want to detect when this is at its peak, you would think that you would just put the value of 1 on the negative input, and every time it hits 1, it will send a pulse out of the output pad here. But there is a little issue with LFOs, and if you have a look here and you see it now reach the top, and if you look very closely, you did not see a value, a number 1 show up there, and that is because of the way the sample rate works in the Zoia, and the way that values are updated, and they're not updated continuously, they have to be updated at certain intervals. And that means there is a possibility that an LFO goes from the value of 0.9997, for instance, and it goes up to 1, and it goes down again to 0.9998, and that is when the next pulse, when the next time the readout is sent to whatever comes next. And that means there is a chance that an LFO, certainly one that has a speed of 1 beat per minute, will never register as a value of 1 exactly. Of course, it will eventually, but it doesn't do it every single time. And that is the key. It needs to trigger every single time, otherwise it won't work. So the solution for this is to set the comparator negative input. I've checked different values, and if I set it to 0.9998, it does always trigger. And that is what we want. It needs to always trigger. It doesn't have to be exactly precise, showing the peak. So now when this goes above 0.9998, it will trigger a value of 1 coming out here from the comparator, and that is sent to a CV flip-flop. What a flip-flop does, it is a switch that can be triggered, and is a latching switch that you can trigger by sending a gate signal. So what I mean by that is that when this input pad here gets a value of 1, or technically it's a value that's higher than 0.5 sent to it, the output of the flip-flop will switch to the opposite phase of what it was. So if it's now is off, If it's off and it gets a pulse in of 1 on the input or a gate signal, a trigger, it will change its value to 1. Let's have a little look here and see when we get to, it'll take a little while now. I'll just keep looking at that so I can see when we get there. So, so when the comparator triggers, it sends a pulse to the flip-flop. The flip-flop turns on, and it stays on until it gets a new gate signal, and that is the key as well to making this work. So the next time it gets a gate signal from the comparator, it will change its value back to 0, and so it will do every flip and flop back and forth. So we're going to have a little look now, and you're getting closer to 1 now. And this comparator should trigger. And there we are, the comparator triggered and the flip-flop switched on. And this is the method for detecting when the LFO here is at its peak. Because when it reaches its peak the first time, we want it to become a negative. We have to invert the phase of the signal. And the second time it reaches its peak, we want it to go back to normal. And that is what this value from the flip-flop is helping us do. I'll get back to where this is connected onwards, but first I'm going to talk about the inverted signal here. So the LFO goes into an inverter, and that is because this is the inverted signal that we want to start using when the LFO reaches its first peak. So what an inverter does is only to change a plus to a minus, basically, or a minus to a plus of what comes in. So here the value from the LFO is always positive, and the value out from the inverter is always negative. And the inverter goes into the second channel of the switch. So the LFO into the first channel of the switch, the inverter into the second channel of the switch. Now, this is an in switch. What an in switch does is it takes a number of inputs, known as what we call them channels, really, or inputs 1 and 2 and 3, etc. You can set it to up to 16 channels. And what it does, the idea behind the switch is that it has a certain number of inputs in the case of an in switch, or outputs in an out switch, and it has a channel select pad that selects between these inputs on an in switch, and then it has an output. And depending on which channel is selected, that channel is the only value that is sent from the input to the output. So the way the channel selector works is it takes the number of channels and it divides the value range from 0 to 1 equally between them. So with 2 channels, the first channel is selected as long as the channel selector gets a value sent to it that is, or it has a value on it, I should say, because you can set an offset in there as well, or you can set it manually on the pad. If it has a value of the things added to it and what is on it, between 0 and 0.5 or 0.4999, I presume. I haven't checked that precisely. And if the value on the channel selector is 0.5 to 1, then it will select channel 2. So in this case, it is quite easy. You make sure that since I've only got 2 channels, what I do is the same as I do with a gate, really. I set it, give it a 0 or a 1. But if you have more channels, you have to make sure, of course, that what value it gets is the one that selects the right channel. I've done this on many other videos before. I do like switches. And if you look here, the flip-flop is the thing that is connected to the channel selector. So that means when the flip-flop is triggered, when it is on, I should say, not when it's triggered, when it's triggered and turns on, then the channel selector gets a value of 1 and it selects channel 2, which is the output from the inverter. So when the flip-flop is on, the inverted signal is the one that is sent out from the switch. When the flip-flop is off, it is the normal signal coming from the LFO that is sent out. So again, in keeping with the diagram I did to start with, when the flip-flop is activated is when the LFO reaches its first peak, and we want to invert it, and therefore we are now sending the negative value out of the switch. I hope that is clear so far. Let's see. Right, so what happens to the signal next? So if you see here, the output from the switch goes to a slew limiter. And this is something that is needed for this to work consistently. And you can see the slew limiter here is connected to two modules. It's connected to the flip-flop and to the in-switch output. If you have a look at the connection strengths now, the in-switch output is connected with a connection strength of 50%, and the output from the flip-flop is connected with 100%. How does that work? Now, you would have thought that at this point you should be able to, instead of going into a slew limiter, you could just send the output now to a value module, and that would be it. But there is one issue with this, and when I did this first, I didn't notice it right away because it does not happen on the first iteration of your patch. But I'll show you, I'll demonstrate on paper again. I'll have a little look. Yeah, so what happens is, okay, so we have our waveform like so, and it turns into this. I'll just explain perhaps first what happens with the so the switch output is 50%, and the reason, of course, is, as I mentioned earlier, we need to reduce the scale here so that the 0 to 1 on the LFO is the same as 0 to 0.5. But what happens next is that it gets a negative number here that needs to be turned into a positive number in a way and get the new output from 0.5 up to 1. So we have the negative output coming from the switch. So let's say we get of course it passes the peak, so it has so at its peak we get first a value of 0.5 coming from the switch, and then the flip-flop activates and you get minus 0.5, but we want that value to become plus 0.5. And the way I do it is by adding the value of the flip-flop. So we get minus 0.5 plus 1 from the flip-flop equals 0.5 again. And as this value goes down from the switch, so you can say it goes to minus 0.4, again it's plus 1 equals 0.6, etc. So then it starts going up here, which is what we wanted to do. And when this value is at 0, of course it's 0 plus 1, so that is when it gets its new peak value. So that's how how that works, how the 50% connection strength from the switch plus the flip-flop makes it get the correct values. But why the slew limiter? That's what I wanted to get to as well. So this is the first generation one where we have 1 minute, and it turns into a new waveform here that is 2 minutes long, and we do 2 of those. And now the problem is that as we get to the peak of the LFO, when it reaches a value of 1 and the flip-flop triggers and the switch triggers, what can happen is you get a little glitch when the value will jump. So if you imagine that at this point here, for a very, very brief moment, and you might not even see it on the screen, because the flip-flop adds its value of 1, there is a possibility that either the negative value is subtracted before the flip-flop comes in, or the flip-flop is added before the negative value comes in. Because it may not happen exactly the same time internally in the Zoia, which means that you get a spike like this up to a value of 1, where if the flip-flop is added first, or you get a spike down to minus, or to 0 rather, or to -1 really, if the inverted value is added first. And if these two things happen at the same time, it could go either way, it seems. But and then what can happen is if this value goes to 1, what can happen is that the comparator triggers again, and it triggers the flip-flop, which will mess up what happens next completely. So that is why when you get to the second thing here, this of course will happen halfway up, because you won't really see it on the first generation, but once you get to the second one here, you will see it, because this point here is going to be 0.5. So what will happen then is that at 0.5 you will get the flip-flop triggering, and instead of going up, it will then start going down again. Let's see, how was it again? It goes like that, and it goes like that, and it goes like that. Something like that, I think, is sort of the waveform you get if I just remove this bit there. Something like that might actually be the waveform you get if you get the those little blips. That's not what you want. If you get that blip, it will mess up the algorithm of the patch. So how do you solve that? Well, that's when the slew limiter comes in. Right, so what is a slew limiter and how does it work? Well, what a slew limiter does is it slows down a change. One way I like thinking about it is that it's always chasing the new value. So when the new value that it's the input of the slew limiter goes up, the slew limiter is trying to catch up, but it's always going to be behind. And that's how it works all the time. It takes the difference between the current output value of the slew limiter and the value of the input, and it's trying to move across that difference in values in its slew time. It's easiest to show this on a square wave, how that looks. So this is a square wave, and let's imagine for a moment that we have a slew time that is the same as 1 square of the peak here of this square wave. So when we are at this point here, we have a slew value of 0, we have an LFO value of 0, but suddenly the LFO goes to 1. And then what the slew limiter does, it is calculates the difference between the value at the output, which is 0, and the value at the input, which is 1, and it takes that range and divides it over time, which is the slew time, and it decides that for every little tick now I have to move a little bit up, and so it starts moving up like so, and that is the new output of the slew limiter. And the same thing happens when you get to the end of the peak here, and the LFO suddenly goes straight down. The slew limiter will take that range and do like so. A little bit wonky this, sorry. And it will keep doing that. If you increase the slew time, of course it will get even more sharp angle like that. And if the slew time is half the length of the LFO time, of course, something interesting happens. You actually get a triangle wave, like so. So, and once you have a triangle wave, of course, if you then increase the slew time even more, this will behave exactly the same way as a triangle wave, actually. I'll just show you now. I'm not going to do the phase precisely now because it's a little bit tricky. So what happens with a triangle wave is when you add slew is that it will flatten. So as you add more slew, I'll just do an illustration next. So I'm not going to do the phase shift now that you get as well, because as you can see, the new peak is now moved as well by the slew limit time. I'm not going to do that here because I don't know exactly where it will be, but I'm going to do like so just to demonstrate. So this is how the slewed wave will look like. It will get compressed. And what that also means is that now at a certain slew amount, which isn't very high, by the way, the wave will not reach 0 and it will not reach a value of 1, which is also quite an interesting effect of using a slew limiter. As an aside, I would like to mention also, if you use a slew limiter in analog circuitry, or just a simple slew limiter, which is basically just a capacitor to ground and a resistor. You also need a resistor, I think, to make that work properly. So a resistor in series and a capacitor to ground. What happens is, unlike the Zoia, which has a linear slew limiter, an analog slew limiter in a capacitor, when it has this difference between the input and the output, it will move faster the further away it is. So basically you get this kind of shape if you use a capacitor in analog circuitry. Of course, it would have been fun to have a slew limiter on the Zoia that does the same thing, but it's quite a different behavior, which is quite interesting, actually. Of course, there are different ways to make slew limiters in analog circuitry, but the simplest by far way of doing it is to use a resistor and capacitor, and that's you, and you get this kind of effect, which is kind of cool, I think. That's the slew limiter, how a slew limiter works. And of course, in our case, we have let's do the wave now, and we have these sudden blips at 0.5 that need sorting out. And of course, these blips are really, really short, so we don't need a lot of slew limiter to sort those out for you. If you zoom in on one of these blips now, so it's really, really zoomed in, and it looks like this, and it's a peak going up like so, and then it goes down again, and then it keeps going up like so. So what we need here, if we have a slew limiter that is only half the length of the glitch, that would be enough to round it off, so it just doesn't get to, because it only needs to stay below 0.9998. So we don't need a lot of slew limiter on this to actually make it reduce it so it doesn't create any harm. And even if you just have a slew limiter that has this kind of length, you're still just rounding off the peak a little bit on the, well, not rounding it off, you're making a point a little bit shorter there, of the waveform. You're still above 0.998 there, but the glitch would be almost gone, pretty much. So this is the principle of it. You reduce the glitch, you add a little bit of a little change in the tip of the LFO, but it's so small you're still well above the 0.9998 line that it needs to be, and this makes it absolutely certain that there is no way that the flip-flop or the comparator and the flip-flop can re-trigger and mess up your patch. I'm really sorry, that was a long explanation, but I hope that made it really clear how that works, because it might not be obvious to everyone watching this. And yeah, I do apologize if you knew how a slew limiter worked really well before this. Anyway, so I've added just 0.10 seconds. I don't think it needs to be that long, to be honest, but when you think about it, 0.10 seconds is a really, really, really short length of time relative to 60 seconds for the cycle of this LFO. And of course, it will get even shorter when you do consecutive ones. You could use other means to slow down the signal, make sure that the change doesn't happen until after a little delay or something like that. But Slew Limiter works really well, and it's an easy way to do it. Right, so that's the output of the Slew Limiter. Is then sent to a value module, and that is the output of this LFO. So this should now have twice the length of this LFO. So this is 60 seconds. This should take 120 seconds to reach its endpoint. And if you just give me a moment here. So first LFO 1 minute, second LFO, second value here is then 2 minutes. So how long can we go? The title might give something away there, but I'm not sure. I haven't decided on the title of this video yet, but I might give something away there. So we take now this value and we move it over here. And then we run through exactly the same process again, starting with a value module here instead of an LFO, and the output is over here now, and that is now, so we see 81, 2, 3, 4, 5, 6, 44, 5, 6, 7, so that's half the speed again, and so that's now 4 minutes, and then we have the next one is 8 minutes, and then we continue. And we have 16 minutes, 32 minutes, 1 hour, 4 minutes, 2 hours, 8 minutes. This is 4 hours, 16 minutes. It's really slow now. 8 hours, 32 minutes. Let's keep going. 17 hours, 4 minutes. 1 day, 10 hours and 8 minutes. 2 days, 20 hours and 16 minutes. 5 days, 16 hours and 32 minutes. 11 days, 9 hours and 4 minutes. 22 days, 18 hours and 8 minutes. 45 days, 12 hours and 16 minutes. 91 days and 32 minutes. 182 days, 1 hour and 4 minutes. And 364 days, 2 hours and 8 minutes, which is almost a year. And of course, the reason this is standing still now is because this only gets one tick, one moving 1/10,000th of a value of a CV value now only once every 52 minutes. So if you were sitting here for 52 minutes, we would be assured that this would move 1 tick. So how far can you go? This is just 1 year, of course, which is probably longer than you need, but and that's all I programmed this one for. So this is 65% now. If all the modules here take up the same space all the time on the CPU, all the same load on the CPU, this is using 65%, and that means you could conceivably squeeze in another 9 or so. So this is 19 iterations of doubling. If you can squeeze in another 9, that means that you can get up to a theoretical maximum with this method, that is, unless you can find a more CPU-friendly way of doing it. This method can give you an LFO that lasts that has a cycle of 512 years. Of course, I've rounded it off now and saying that actually it could get longer probably, but if you start with, it would get longer if you used 88 seconds instead of 60 seconds for the cycle to start with. But just for simplicity's sake, if you use 1 beat per minute to start with, you would have roughly 512 years of one cycle of LFO on this. So that is possible. Ridiculous, of course, not very useful to have a 512-year LFO. It's nice to know that you can. At least it is a way to overcome another seeming limitation of the Zoia to be able to create longer LFOs. So while 512-year LFOs or even 1-year LFOs might not be that useful, having an LFO that's longer than 88 seconds, on the other hand, can be really useful. So this is a method, one possible method of doing that is quite simple to program and easy to implement in your own patches. So that's really all I wanted to show you today, and I think I should round it off here before I lose my voice. As you can hear, I'm losing my voice from all this talking. I also did some other videos earlier today, and I've been talking all day basically. If you enjoyed this, if there was something in this video and this patch that you learned from, something you might want to use in your own patches, of course, you may get other ideas just from the way this is, the algorithm of it, from the way it's patched together, from the use of a slew limiter to clean the transition between signals that jump. If you found it useful and if you enjoyed it, indeed, please like, share, comment, subscribe, and join me on Patreon if you like. I will see you again in my next video. So thank you very much for watching, and goodbye for now.